So, good afternoon students, once again welcome back to chemistry online classes. Now see, yesterday we have completed 16 group elements, right? That is manufacture of sulfuric acid by contact process, its physical properties, its chemical properties, right? And at the same time oxo acids of the phosphorus and along with the uses of the sulfuric acid we have completed, right? Okay, now today's in this class I will try to start with the 17 group elements. See 15, 16, two groups are over, now 17 and 18 lastly. Okay, in the 17 group elements these are called as, you already know, 17 group elements these are called as halogens. Halogens. Okay, means salt forming elements. Salt forming elements. They are called as salt forming elements. Right. Okay. Now, what are the salt forming elements? What they include? Halogens belongs to 17 group. You know, fluorine, bromine, iodine, and acetone. Fluorine, chlorine, bromine, iodine, and acetone. Right? The atomic number of fluorine is 9. 9 plus 8, 17, 17 plus 18, 35, 35 plus 18, 53, 53 plus 32, 85. And acetone 18 is the radioactive, that is halogen. Right now, as usual, these halogens, they are most electronegative elements in the whole periodic table. And most electronegative element in the periodic table is fluorine, that is fluorine, most electronegative. And these all halogens, they are having 7 valence electron in the outermost orbit, having general electronic configuration NS2, NP5, and they are in deficient of only one electron to become stable, right? That's why due to half-filled orbitals, they are having high ionization energy and they gain extra stability. Let us see what are compounds. First, as usual, sources. What are the sources of fluorine, bromine, and iodine? Generally, fluorine exists in the compound form, that is fluorspar. Okay, very important. It is called calcium chloride, CaF2. Okay, then cryolide, Na3Al6. Ore of aluminium, it does not contain oxygen, that is cryolide, Na3Al6. AlF3, NaF3, okay, combination Na3Al6. Then fluoroptide, okay, 3Ca3PO4 taken twice, right? 3Ca, yeah. You already know, this is fluoroptide. Like this, fluorine exists in the form of its compound state in the form of ores as fluorspar, calcium chloride, cryolide, Na3Al6, and fluoroptide, 3Ca3PO4 taken twice, dot Ca. Okay. And not only this, even chlorine and bromine. Combinedly, they are available in the form of the compounds. The respective fluorides as well as bromides. Okay. Then coming to next source of chlorine. How chlorine exists in the nature? How chlorine? Like that of chlorine, that means especially these are in combined form. Seawater. Especially seawater contains the chlorides and fluorides. Fluorine is fairly abundant, but this seawater contains chlorides, bromides, iodides. Okay, seawater contains chlorides, bromides, iodides, and also apart from chloride, bromides, and iodide, this iodides of sodium, potassium, magnesium and calcium. And maybe sodium chloride NaCl 2.5% by mass, that is C1. Very important for CET purpose. That means chloride, bromide, they are in the form of respective metal salts, sodium chloride, bromide or sodium iodide. That's what chloride, bromide, iodides, they exist of the sodium, potassium, magnesium and calcium in the seawater. But high percentage is a chloride, sodium chloride, that is 2.5% by mass. Right? Now let us go for bromide. How bromine exists? The deposits of the dried up sea contains mainly KCl, such called silver, and KCl, MgCl2, 6H2, hexahydrated potassium magnesium chloride, this is called carnarine. Okay, like this in compound form they are present. At acetylene is usually that is a radioactive, that is what you call it as halogen. Like this in the nature, these chlorides, bromides, iodides, they are all crystalline solids and mainly they are content of the sea only. They are content of sea only. This is about the source, but mainly fluorine with this as fluorspar, rhyolite, fluoride. This is once again very important for 1 marks, even for theory as well as need. Try to remember for maintenance. Okay? That this is regarding source. Now once again as usual, after source now we can go for their general electronic configuration. Let us see. So general electronic configuration of these halogens, you know what is that? Fluorine as atomic number 9, 1s2, 2s2, 2p5. Like this, 1s2, 2s2, 2p6, 3s2, 3p5. Like this bromine, 1s2, 2s2, 2p6, 3s2, 3p6, 3p10, okay, 4s2, 4p5, right, bromine. Then iodine, 1s2, 2s2, 2p6, 3s2, 3p6, 3p10, as well 4s2, 4p6, 4d10, finally 5s2, 5p5. That is iodine. And lastly, acetylene, 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, right? Then 4s2, 4p6, 4d10, 4f14, okay, 5s2, 5p6, 5d10, then 6s2, 6p5. Right, so like this we can write. Okay, so this we can also write it as shortly as, that is argon, this is krypton up to here, and this is up to, that is xenon. Like this, generally we can get it. Okay. Then 18, 28, 36, 46, 46, 60. After xenon we can write for a 14 and 5s2 up to 4p6. So like this, students, we can write general electronic configuration of see here neon, argon, krypton and here xenon. Nobody, not necessary That's what. See, if you ends with 2s to 2p5, similarly 3s to 3p5, 4s to 4p5, 5s to 5p5, 6s to 6p5. Only for this purpose I have written this. Okay, otherwise you can use also inert gas configuration. Right. Now what is the general electronic configuration? Ns to Np5 is the general electronic configuration of 17th group of elements. So how we have for 15th group Ns to Np3 and 16th group Ns to Np4, 17th group Ns to Np5. 15th group once again Vicogens, 16th group Chalcogens and 17th group Halogens. Right? Okay. Now this completes the general electronic configuration of the elements. Now based on this variation of same atomic radii of the 17 group elements, as they are most electropositive elements in the periodic table, from fluorine to astatine, atomic size increases, atomic radii increases. Right? But when we take individually across the period, these 17 group elements are having smaller atomic radii than 16th and 15th, even 14th and 13th group elements. They are having smaller atomic radii in the p block elements. Why? Because along the period effective nuclear charge increases, non-metallic character increases. Right? Therefore, atomic radii decreases. Across the period, they are smaller atomic radii, but down the group from fluorine to iodine or astatine, atomic radii increases due to increase in size. That's it. But that increase in size is not regular. Once again, due to here imperfect shading of 3D, imperfect shading of 4D, and imperfect shading of 4F. That is 4F electrons as usual. It is applicable for all 15, 16, and 17 group. Common, very easy to remember. What I told you, imperfect shielding of 3D, 4D, 4F. Okay. Right. Now after this atomic radii, let us move on to next property, ionization enthalpy. Ionization enthalpy. For ionization enthalpy or ionization energy, you know that atomic radii increases down the group, therefore ionization energy decreases because they inversely proportional from fluorine to astatine. But these halogens, they are having extremely abnormally, or they are having higher ionization energy compared to 16, 15, 14 and 13. Why? Because they are in deficient of only one electron to acquire nearest noble gas configuration, and they are highly electronegative element. They have their electron accepting tendency is strongest in the whole periodic table. That's why ionization energy are high compared to other elements of the period. Okay, but down the group as usual decreases with increase in size. That's it. Okay, that's about ionization enthalpy. After ionization enthalpy, say electronegativity. In electronegativity, just see here, students, fluorine is the most electronegative element in the whole periodic table because of smaller atomic size. Then followed by the second actually oxygen, then chlorine, bromine, iodine and astatine. Okay, down the group electronegativity decreases. But these are the most electronegative elements in the whole periodic table. Highest electronegative element is fluorine. Remember, for 1 marks, important. And already studied in periodicity of elements in the last year in periodicity of elements. After electronegativity, once again electron gain enthalpy. Electron gain enthalpy is the absolute tendency of electron to attract the bonded pair of electron towards itself. Absolute tendency. But electronegativity is the relative tendency. So this electron gain enthalpy also is what that is from fluorine generally to astatine should decrease. But thing is, chlorine is having higher electron gain enthalpy than fluorine. I repeat, fluorine is having less electron gain enthalpy than fluorine, but fluorine is more than bromine. Electron gain enthalpy follows this order. That is, first fluorine is less than chlorine, but chlorine is greater than bromine, bromine is greater than iodine and acetylene. Okay? Why? Chlorine is having smaller electron gain enthalpy than chlorine. Here for 1 mass question, the most electron gain affinity, that means EA electron affinity is greatest for chlorine, not fluorine. Chlorine is having highest electronegativity, but smaller electron gain enthalpy than chlorine. Why? Because of once again size. Due to smaller size, due to smaller size, atomic number 9, that is, electrons are tightly bound to the nucleus. That's why, if for incoming electron, they have what? Electron repulsion due to inter-repulsion of electrons for the incoming electron. Why? Due to small size. Okay. Heat liberated is less. Instead of having attraction, it is having repulsion due to small size. That's why electron gain enthalpy of fluorine is smaller than chlorine, or electron gain enthalpy is higher than fluorine. Why? Because here, if you go down the group, size increases. That attraction for incoming electron increases from chlorine to bromine to iodine. Only for fluorine it is exceptional. Got it? Okay. How in the 16 group oxygen? It is having smaller than sulfur. Like that here, fluorine is having smaller than that is chlorine. Okay? Right. So that's about electron gain enthalpy. It is also very important for 2 marks. 2 marks where in the theory. Okay? Right. When they ask you what you will write, electron gain enthalpy of fluorine is smaller than, that is chlorine, due to smaller atomic size. The incoming electron experiences repulsion rather than attraction. Very simple. Okay? Now after this, normal atomic radii, annihilation enthalpy, electronegativity, electron gain enthalpy. See, non-metallic character definitely decreases down the group. And these are the most electronegative elements. And higher ionization enthalpy. Why? Because they are deficient of only 1 electron to complete the octet structure. Right? That's all about physical properties. Okay, then regarding physical existence, after understanding atomic radii, annihilation enthalpy, electronegativity, electron gain enthalpy, right? Physical properties, how they exist in the nature of nature. Chlorine, all they exist generally as diatomic gases, but they are colored, especially chlorine, they are gases. Okay, bromine, liquid, chlorine, gas, liquid. Iodine is a sublimate solid, or you can tell solid sublimate. Acetylene is also, that is, solid, as the physical state is concerned. Right? Okay, even this fluorine is having green color. That is, fluorine is having somewhat, that is, color of fluorine is mainly due to 1 unpaired electron, absorption of light. Fluorine is yellow in color, and this is greenish yellow. Okay, and this is reddish brown in color, and iodine violet vapors. Okay, this is due to emission and absorption of electrons from the visible region. They absorb and in turn they will give complementary color, that's emit light, that is the yellow light by the fluorine gas, chlorine greenish yellow color, reddish brown color, bromine, and iodine, that is violet vapors. But generally it exists in the form of what? Diatomic, F2, Cl2, Br2, I2. They are homonuclear diatomic molecules containing single covalent bonds. Okay, fluorine, that is yellow color, chlorine electron, pungent odor, iodine, violet peppers, highly pungent odor. But see, these are all soluble, extremely soluble in water. Fluorine, chlorine, highly soluble in water. But bromine and iodine, they are sparingly soluble, but their solubility is very much high in organic solvents like carbon tetrachloride, carbon disulfide and alcohol, but sparingly soluble in water. For the first two halogens, fluorine, chlorine, they are highly soluble in water due to intermolecular hydrogen bonding. Remember, okay, fluorine especially, not chlorine, right? Right. So that's about physical existence. They are diatomic, no doubt. First two readily soluble, then sparingly soluble in organic solvents. And this is about their colors due to emission and absorption of light by the electrons, outermost one unpaired electron. That is responsible, right? Okay. So that's about physical properties. Okay. After the green color, right, solubility, physical existence. Another one is they react with water. That's what I already told you. Bond dissociation energy, very important. Bond dissociation energy, BDE. Bond dissociation energy, BDE. Bond dissociation energy of chlorine and bromine. F2, Cl2, Br2 and Cl2. When we follow, fluorine is less than bromine, but bromine greater than, that is fluorine, bromine, iodine. They follow this. Bond dissociation of energy of fluorine is less. Why? Because of smaller size, less than 2. Electron gain enthalpy. Because of smaller size, bond can be broken very easily, highly ionic. Right? Because of this, bond dissociation energy of fluorine is smaller than due to smaller atomic size and interrepulsion. Repulsion for incoming electron. That's why bond dissociation energy actually should be more, okay? Because of size, no, but due to repulsion, it can be broken very easily. That's why fluorine is having smaller dissociation energy than chlorine, but as usual, once again it decreases from chlorine to iodine. That's about BDE, bond dissociation energy. After bond dissociation energy, reactivity water, colors are already told you. Okay, now we'll move on to that is after this all physical properties. Now available in chemical properties, oxidation state. Oxidation state. Right. These halogens, as per their oxidation state is concerned, mainly chlorine, bromine, iodine, all they exhibit commonly -1 oxidation state in their hydride forms. Apart from -1, they are having higher variable oxidation state. +1, +3, +5, +1. Ground state electronic configuration generally is +1. First excited state +3, second excited state +5, and the third excited state is +7. Because you know that general electronic configuration of these halogens is what? Ns2 Np5. When you write outer electronic configuration, Ns2 Np5. See, pH1, Py1, Pz1, pH2, Py2. This is 2Pz1. If it bears here, -1. If it loses, +1. Okay? Then, first excited state, 2s electron get excited to where 1, 2, 2p x2, 2p y2. This is already filled. Will jump to 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. See, like this. 1, 2, 3. Plus 3. Got it? Now, next, these electrons also jump to this electron if it jumps to higher energy levels. 1, 2, 3, 4, 5. Okay? After NS, NP, and this is ND. ND, NS. NS, NP, ND. Right? Okay, last is third excited state. Even this electron also. 1, 2, okay? Or until this also will get excited to ND. 1, 2, 3, 4, 5. 1, 2, 3. Got it? Like this, first excited state plus 3, second excited state plus 5, right? And third excited state plus 7. So in this way, these halogens in first excited state they exhibit plus 3, second plus 5, and third plus 7. But normally minus 1 and plus 1. Okay? This is about the oxidation state exhibited by halogens. Now just I will give you some examples. For example, here is an oxo acids, hypochlorous acid HClO, chlorous acid HClO2, chloric acid HClO3, perchloric acid HClO4. That's only plus 1, plus 3, plus 5, plus 1. Okay? ClF, ClF2, ClF3, ClF5, and ClF7 doesn't exist. Plus 1, okay, and here plus 3, plus 5 maximum. These are called interhalogen compounds, right? Interhalogen compounds, right? And generally these are called oxo acids of the chlorine. Okay, like this they are having a variable oxidation state that you will come to know once again in interhalogen compounds in detail. So that's about oxidation state exhibited by these particular elements. Not only this, even see, that's some iodine, pentafluoride, bromine, pentafluoride is also plus 7 oxidation state, plus 5 oxidation state. Even bromine also, not iodine, even not chlorine, even bromine also. That means except the fluorine, fluorine can exhibit minus 1, plus 1. Minus 1, plus 1 at the most plus 2. But apart from fluorine, all elements exhibit plus 3, plus 5, plus 7 in first excited state, second excited state, and third excited states. Okay? So that's about the oxidation state. But this once again oxidation state from fluorine to iodine to fluorine, chlorine, bromine to iodine, down the group, becomes stable due to inert pair effect as well. And they are stable, especially these halogens are stable with plus 1 oxidation state. Okay, fluorine at the most, chlorine plus 3, but plus 5 at the most, but plus 7 becomes unstable due to inert pair effect. First two elements, fluorine will never because absence of d orbitals. It can form only one mono ox, that is hypochlorous acid HFO, but never form more than that. That's why chlorine it can form plus 7, stable. But after chlorine, bromine, iodine, and bromine and iodine they become stable at plus 5 due to inert pair effect. Inert pair effect. Here also it is applicable. Now we applied for 15 and 16 group. What is inert pair effect? The reluctance of NS electron in chemical bond formation compared to NP electrons, as NS electrons are highly diffused into nucleus. Right? Due to inert pair effect, plus 5 becomes stable for bromine and iodine. Plus 7 becomes stable for chlorine, not fluorine. Right? Keep this in mind. That's about oxidation state exhibited by this particular halogens. That means see 15 group I told you, minus 3 to plus 1. Right? 16 group minus 2 plus 2 plus 4 plus 6. Like the 17 group here, minus 1 plus 1 plus 3 plus 5 plus 7. Okay, like this I will remember. Okay. Then afterwards, after understanding physical properties, chemical properties, that is one chemical property, oxidation state. Now it's a turn of very important, another important property here. These halogens, they are having one another important unique character addition here. Apart from, before going to reactivity with the hydrogen, oxidizing power. Oxidizing power. These are having most. That means these halogens, they act as powerful oxidizing agent in the whole periodic table. In the diatomic form, they act as powerful oxidizing agents. What is an oxidizing agent? It's electron pair donor. Acceptor. Electron pair acceptor is oxidizing agent, whereas electron pair donor is reducing agent according to modern electronic interpretation theory. So this fluorine, chlorine, bromine, remember. That is what? Oxidizing property. Very important picture. Oxidizing property. Important for theory purpose. For 2 marks theory. Even for CED also, just I will tell you what is important. Fluorine, okay, is having plus 2.87 volts E0 value in potential. Standard electrode potential value. Fluorine plus 1.54 volts. Okay, bromine plus 1.09 volts, and iodine, that is plus 0.54 volts. That means what is this E0? Standard electrode potential that you already studied in the electrochemistry. Higher the positive reduction potential or standard reduction potential, most powerful oxidizing agent. That means they have high tendency to accept. Why? Because they are more electronegative. See, electron को अपनी तरफ खींचना, खींचिंग effect I already told you. What is electronegativity? Electronegativity is the attraction of bonding pair of electron or shared pair of electron towards itself. It is high. Why? Because of this higher standard reduction potential value. But from fluorine to bromine iodine down the road, this oxidizing nature decreases. Let us take some example. See, fluorine can displace fluorine from potassium chloride. Why? Because oxidizing nature is more. So it can displace mixer. Cl2 will come out from 2Kf, 2KCl. Even fluorine can displace bromine, KPr. Here also same thing. What you will get? Bromine come outside, will form 2Kf. Not only this, even fluorine can displace not only bromine, even iodine also. 2Ki, 2I2, along with the 2Kf. That means fluorine displaces fluorine, bromine, iodine from their salt solution. Why? Because powerful oxidizing agent. Means which is having above, that will displace below from their salt solution. Very important for CCET. So many times repeated. Even for NEET also. These reactions are important. Okay. Coming to next chlorine. See, chlorine can displace only bromine below it, 2 kBr from its salt solution, that is Br plus 2 Kc. Okay, and chlorine can displace iodine Ki, 2 Ki and 2 Kc. Next, bromine can displace Br2 can displace iodine from salt solution. Okay, 2 kBr. But iodine cannot displace any of the compound. Like this, reducing power decreases. Not only this, even this can also be explained on the basis of very importantly oxidizing power, reactivity with the water. See, reactivity with the water, fluorine react with the 2 moles of water and can form 4 HF and liberates 4. So it displaces 4. Not only that, even right? Fix HF and fluorine, sorry, 3F2 plus 3H2O. Okay, that is O3. That is O3. See, like this, it is highly reactive in the nature. Not only this, even the fluorine also dissolves in water to form, undergo this proportion to form HClO and HCl. HClO and HCl, hypochlorous acid and hydrochloric acid, +1, -1. This proportion is a reaction. These reactions also shows that fluorine and chlorine, they are powerful oxidizing agents, strongest oxidizing agents. From bromine to iodine, generally it decreases due to inert pair effect and also due to decrease in standard electrode potential value. Remember, okay? Right, so that's about oxidizing property. Very important as far halogen is concerned. It is exhibited by only halogens, not 15 and 16 group elements. Remember, because these are the most electronegative elements in the whole periodic table, highly reactive because of electronegative power. That's only that power is mainly due to what? This standard reduction potential, the potential attained by metal when metal is in equilibrium with its own ions at a 25 degrees Celsius temperature or 200 Kelvin temperature, having concentration 1 molar, is called standard electrode potential, SEP, or standard reduction potential. They are having positive value, they act as good oxidizing agents. If they are having negative value, they act as good reducing agent. And repeat, oxidizing agent is electron acceptor and reducing agent is electron donor. Remember, okay? That's about oxidizing power, oxidizing properties of the halogens. See, that means in 17 group, 2 properties, unique properties are extra. What are those? Electron gain enthalpy, bond dissociation energy of fluorine. Right? And its oxidizing property, which is a very important. And commonly in Karnataka CET they are repeated so many times, compulsory one these reactions, which is not possible, or which is possible, which can displace other elements. These are possible. But see, bromine, remember, bromine cannot displace, no reaction, right? Reaction potential is less, right? Sorry, extremely sorry. Iodine cannot displace K, potassium at the least. Okay, and that's about oxidizing properties of the halogens. And even remember, oxidizing property can also be given as dissociation energy. X2 gas dissociate to form X gas, generally from, okay, that is X minus. Further, they are dissolved in water to form, that is X minus aqueous, right? Fluorine to fluoride, fluoride in gaseous state too, that is in aqueous state, that is F minus. But all in F. Here dissociation energy, here electron gain enthalpy, and here hydration energy. Remember, that will come to know very clearly later. That's the properties of halogens. That's the properties of halogens. Okay. Right. Now coming to next after this oxidizing property. Right. Now what is remaining, students? Chemical properties. In chemical properties, once again as well. This is one extra we have discussed. Now we shall go for what? Reactivity with hydrogen. All these elements react with the hydrogen. See, fluorine, bromine, iodine. Except acetylene, because acetylene is radioactive. What? Hydrogen. Fluorine will form HF, hydrogen fluoride. Chlorine, HCl, hydrogen chloride. Bromine, hydrogen bromide. Iodine, hydrogen iodide. The hydride formed by the 17 group elements are hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide. In this condition, we are not having any Plus and minus, unit positive and unit negative charges you don't have because they are held by covalent bond. Single covalent bond, already studied in Lewis dot structure. But when they are dissolved in polar solvent like water, then they will dissociate to form H plus F minus, H plus Cl minus, H plus Br minus, H plus I minus. That means then they are called hydrofluoric acid, hydrochloric acid, hydrochromic acid, hydroiodic acid. When they are dissolved in aqueous solvent like water. Remember, polarity is induced in them only by addition of water, not in this situation. Okay? And once again, the hydrides, stability of these hydrides once again decreases. Okay, decreases down the road. Decreases down the road. Why? Because of decrease in bond dissociation energy from hydrogen fluoride to hydrogen iodide. See. Smaller size, bond dissociation energy is more. The size increases, bond dissociation decreases, stability decreases. Now what about acidic property? Acidic property also HF is less acidic than HCl, is less acidic than HBr, is less acidic than HI. Okay? That means except this HF, because of the high bond dissociation energy. Because of the high bond dissociation energy, it is highly ionic in the nature. But as far as acidic property is concerned, acidic strength in general if it concerned, that's only they follow this order: HF, HCl, HBr, and HI. See, as the size increases, the release of proton becomes easy. So acidic property increases. If acidic property increases, reducing nature also. Reducing property follows the same. HF, okay, less than HCl, HBr, HI. Same means HI is the strongest, HF is the least reducing agent because it is a powerful oxidizing agent. Okay, this is now stability, acidic property, and reducing nature. Then what about basicity, students? Basicity of these halogens. Stability over. Okay, reducing nature increases from HF to HI, that is given. Now what about ionic character? Ionic character, that's important. Ionic character follows this order. Ionic character, HF is greater than HCl, is greater than HBr, is greater than HI. Why? Because as the size of halogen, anion increases, covalent character increases, ionic character decreases. Therefore, highest ionic is HF, lowest ionic is HI. That is the most covalent, least ionic. This is the highest, most ionic, least covalent. In the first year, we studied the Poisson's rule: larger size of ion, more the covalent character. Therefore, HI is more covalent than HBr. HBr is more covalent than HCl. HCl is more covalent than HF. Smaller size, that's due to bond dissociation, smaller bond dissociation energy. Okay, HF is more ionic than HCl. HCl is more ionic than HBr. HBr is more ionic than HI. So that's about reactivity of these halogens with the hydrogen. Okay, with the hydrogen. The hydride formed by the halogens are hydrofluoric acid, hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide. But remember, HF exists in the form of especially liquid state. Why? Due to intermolecular hydrogen bonding and high ionic character. HCl, HBr, HI, they are all gases. Okay? Because they do not form intermolecular hydrogen bonding. That's most important question for 1 marks. HF is liquid, HCl is gas, give reason, due to intermolecular hydrogen bonding. And even melting point and boiling point of HF is greater than HCl, HBr and HI due to exceptionally due to intermolecular hydrogen bonding. Okay, that's about reactivity with the hydrogen. See students, today we'll stop here. Why? Because we have learned so so that it can't gets confusion. So I have covered first sources as usual, then general electronic configuration, then afterwards variation of atomic radii, ionization enthalpy, electron gain enthalpy, okay, even electronegativity, and these are non-metallic, most electronegative, highest ionization energy, right? Then afterwards their physical state I told you, color exhibited by them I told you, reactivity with the water, okay, even generally I discuss with the oxidation state exhibited by them, variable oxidation state, apart from additionally bond dissociation energy and oxidizing property, and lastly this one important chemical property is the reactivity with the hydrogen. In the same manner, they also react with oxygen and halogens and form the respective oxides and interhalogen compounds. That I will discuss tomorrow without making any hurry. Tomorrow we will complete that, and anomalous property, then we will go for first compound fluorine. Okay. So for today we will stop here. Thank you and enjoy the day. Thanks from PANCHNATH.